Hello there, Mr. Chan here for Algebra 1. Welcome back. We're going to do lesson 6-1. Grab your EnVision Student Companion note taker and turn to page 115. Get ready for some new materials today. It's going to be kind of shocking and exciting at the same time. 6-1. It's called Rational Exponents and Properties of Exponents. Now, before we get started here with the actual opener, I would like to take some space at the top of the page and write out some properties that hopefully you are familiar with from your previous math class when it comes to exponent properties, okay? So here we go. Write this at the top. Exponent properties. Now, let's just do some examples here. What if you're presented with, say, x to the third times x squared, all right? Let me zoom in a little bit so you can see a little better. Well, when you first learned what these things mean, you broke it down into its factors. X to the third literally meant x, because there's 3 of them, and x squared literally means x. And you counted them up. Oh, there are 5 of them. Literally. So that told you that the rule is to add the exponents. That was the rule. When it comes to multiplying exponents. X to the third times x squared. Then you probably went on and did a problem like this. X to the third divided by x squared. Oh, we're dividing here. This literally means x in the numerator divided by x in the denominator. And when you reduce that, you're left with a single x, or x to the first. Just like the last one, the exponents are related, in this case, by subtracting them. Okay? Here you subtract. That's the rule there. The previous one you added, forgot to circle those numbers up there, okay? So when you're multiplying, you add the exponents. When you're dividing, you subtract the exponents. And then finally, you probably learned one other major property when it comes to exponents. What if you had a problem like this? X to the third, and then you parenthesize that and you squared it. Now, x to the third squared is called a power of a power. And this is where you literally wrote it out like this. X to the third, oops, yeah. Times x to the third, and that becomes x times x. And in this case, we have a total of x to the 6th number of things, of x's. X to the 6th. How does the number 3 and 2 and 6 relate? Oh, here you multiply the exponents. That was the rule. Those are the 3 major rules you learned in your previous math class. The first one was called the product of a power. The second one was a quotient of a power. And the third one we just did is called the power of a power. Those are the 3 rules. Now today, we are going to go a little further and explore what happens when we apply some of these rules, but we get something unusual. Okay, so watch this. Right there. We're kind of using all the space around this before we actually start the actual opener. What if we had x to the third divided by x to the fifth? This is the strange one. Well, we know x to the third is x, x, x. And x to the fifth, of course, is x, 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 x. Let's show that here. And when you cancel, oh, you're left with 1 over xx, or literally 1 over x squared. Somehow the answer has the x's in the denominator. If we had followed the quotient rule of subtracting, in this case the numerator and the denominator, we would get, I mean, if we followed it to the t, technically we should have gotten, interesting, x to the negative 2 power. What? 3 minus 5 is negative 2? That's a weird answer, isn't it? Very strange. In fact, that is called a negative exponent. Write that down. In math, a negative exponent doesn't mean the answer is negative. It means for you to do something with the base, meaning the variable x. This somehow is the same as that. And that's what you need to think about. Da, 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 da. I'm about to give you a new property of exponents. We've already gotten the product property, the quotient property, and the power of power property. We are now going to show you the negative exponents rule. Okay, so hold on to that thought there with x to the negative 2. If you ever get a negative exponent, a, let's just use a generically, to the negative m power, this will equal to 1 over, or 1 divided by a to the m. In a way, we are kind of, it's called reciprocating the base. That is the key with the negative exponents. With the negative exponent, the rule is to reciprocate the base. Reciprocate means to move it to the opposite side of the fraction. The base is the number, the variable in this case. When you reciprocate, if it's up here, you move it down here, and so on and so forth. Think of a 2-story house like a fraction. Think of a negative exponent that's upstairs, goes downstairs. If it's downstairs, you go upstairs in this fraction. I created a fraction there, a to the negative m, and put it over 1 and made it a 2-story house. To apply the negative exponent rule, you move it to the opposite floor, or in this case, in the denominator. We'll have cases where we'll have negative exponents in the denominator, and those get pushed up to the numerator, and the power becomes positive. Okay, once you move the floors, it becomes the opposite power. Isn't that kind of strange? This is called a negative exponent property. Negative does not mean it's a negative answer. Okay, keep that in mind. So literally, that's what happened up here. You were literally moving it downstairs or in the denominator. And that's how we got this as an answer when we expanded x to the third divided by x to the fifth. All right, Woo! That's a lot to absorb, isn't it? Okay, so we got 4 properties so far. There's one more property I want to remind you of, or show you actually. What happens if you have a power that is not negative, not positive, but what if it was 0? That's kind of weird, huh? A to the 0 power equals what is the question? So we'll explore that here a second. The 0 property, 0 power. What is that going to be? Now, a situation like that happens when you get something like this. What if you have x squared over x squared? X squared over x squared literally is division. The rule for division is to subtract the exponents, right? 2 minus 2 is 0. X to the 0. Now, if I were to back up a little bit and expand x squared, I get x over xx over xx. Don't those cancel out and leave you with a bunch of 1s? 1 over 1 over 1 over 1 is 1. Ladies and gentlemen, I just proved to you if you have something divided by itself, literally in this case x squared over x squared, literally got an answer of 0, that literally means it equals to 1 as an answer. Anything to the 0 power is 1, ladies and gentlemen. Dun, 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 dun. Anything to the 0 power is 1. So some of you may have seen this before in your last math class. I just want to now show you that these are 5 properties that you should be aware of for exponents, powers. Hey, let's take a look at what Casey and Jacinta are doing right here, off to the left. Students are asked to write an equivalent expression for 3 to the negative 3rd power. That's kind of weird. 3 to the negative 3rd. Casey and Jacinta each write an expression on the board. 3 to the negative 3rd for Casey is equal to negative 27, interesting. And Jacinta is 3 to the negative 3rd equals 1 over 27. Now let's take that, let me zoom in a little bit so you can see 3 to the negative 3rd using the negative exponent property there. I'm going to put that over 1. I'm going to reciprocate it, the base, and move it downstairs, so to speak. From the numerator to the denominator, I now get 1 over 3 to the 3rd. Aha, 3 to the 3rd is 3 times 3 times 3, and that's simply 1 over 27. Now, that kind of reminds me, we might not start thinking about perfect squares and perfect cubes. So right off the bat here, Casey's wrong. He assumed the answer is negative. That's wrong. It's not negative. It just means to reciprocate. Jacinta is correct. She is correct. And just make note here, who is correct? Obviously Jacinta, not Casey. And make note, a negative exponent does not mean it's a negative answer. All right, very important, this concept. I know sometimes in math they use symbols that mean different things. In this case, a negative exponent does not mean it's a negative answer. I kind of hate that about math, but you know, we just have to be aware of that. There are only so many symbols that you can use out there. Before we move on, I want to just do a quick list, perhaps, of perfect squares and perfect cubes, and the reason why is because they're going to show up in this particular chapter, chapter 6. Let's take a look at some squares. Squares are literally these shapes right here. It's 2-dimension, right? And some squares that pop into my head when you start taking an integer and bringing it into power of 2, you know, so on and so forth. Whoops. My list starts with this: 1, 4, 9. We're talking about 1 times 1, 2 times 2, 3 times 3, 4 times 4, 5 times 5, or 5 squared, 6 squared. And it's good to make a list to kind of see the numbers. 7 squared, 8 squared, 9 squared, and so on. Let's make the lists. And these numbers you should recognize from maybe your days in 4th grade or 5th grade. Okay? Yeah, I'll stop there. That's good. How about some cubes? Cubes is 3-dimensional. It's a length and a width and a height. So a cube looks like this. You're actually getting a volume. In geometry, you'll learn in the future that a cube is technically called a rectangular prism. Sounds kind of weird, huh? Rectangular meaning the base, prism means it gets extended in that direction. What if we bring these integers to a 3rd power? Ooh. Gets kind of hairy there. Here are the numbers that I know of. 1. 2 times 2 times 2 is 8. 3 times 3 times 3, we just got 27. 4 times 4 times 4 is 64. 5 times 5 times 5 is 125. Holy cow, 6 times 6 times 6 is 216. So in your future, you might be asked to memorize some of these cubes or figure it out on your computer, calculator. Okay? All right. Before we move on, let's do a quick secondary example just for fun. I have some space right here. What if I ask you to find what 5 to the -2 power is? It's just like 3 to the -3rd. There's a negative exponent. Best thing to do if you don't have a fraction is to make it a fraction first. And we're basically going to reciprocate, yeah? We're going to flip it, right? Move it to the opposite part of the fraction. So this equals 1 over 5 squared. 1 over 5 squared is 1 over 25. Let me know if you have any questions, of course. All right. I'm not going to do B, but I'm going to throw in a relationship when it comes to powers and radicals, okay? Because this is going to set me up for the next page. This is very important now. So are there any questions about our little opener, a little review of the properties of exponents? There's a lot. There's 5 of them. Product, quotient, power. We have negative exponents, and we have 0 exponents or powers, okay? And by the way, those are the same words, by the way. Power and exponent mean the same thing, and I apologize if I neglected to say that. Powers and exponents are the same. Okay. So, just like adding, subtracting, multiplying, dividing, powers also have their inverse functions, right? Add is opposite of subtract, multiplication is opposite of division. Powers opposite are roots. When you say 3 squared, you're literally saying 3 times 3. Of course, we know that is 9. What if we go backwards? The opposite of square, in this case, is called square root. And that symbol should look familiar right here. Square root of the answer I just got right here of 9, that's what that means right there. This means square root, which is the opposite function of square, literally means, hey, what times what will give you 9? So in this case, we would break it down into its prime factors. We know that 9 is 3 times 3, and we're looking for a pair. Hey, there's my pair, yay. That gets to come out of the radical. And that gives me an answer of 3. 3 is the square root of 9. Okay, just a nice little review of how they are inverse operations of each other, square and square root. So with that in mind, we're going to get into some complex type of problem solving in this chapter involving powers. What if we start giving you some algebraic problems where, what if I give something like this to you? 5, let's throw these into equations, by the way, because right now we're looking for equivalent expressions. What if I have 5 to, I'm going to throw in some algebra here, x plus 1 equals to 5 to the 4th power. Wow, I just threw something crazy at you. Now, before you go worrying about this whole thing, notice it's an equation. Yeah, there's an equal sign. And you notice that the bases, those are bases, are the same. Because the bases are the same, it's actually not that bad. You just focus your eye on the powers. That's it. Just solve it like a regular equation. When the bases are the same, focus on the powers. In this case, x plus 1 equals 4. Treat it like an equation, subtract 1 to both sides. That's it. I know. X equals 3. That's your answer. That's it. We're just trying to present problems to you in a different way. They just happen to hide some algebra in the exponent part. So that gives me here a property for you. It's called the one-to-one property of exponents. If you have a base in an equation equal to the same base in the other side of the equation, then you can focus on the powers itself when the bases are the same. So that's really cool. Just focus on that, okay? Very easy. This is called the one, in other books they used to call this the one-to-one property of exponents. This book doesn't call it anything. How are we doing out there? Woo! All right. I think this is a pretty big introduction. Yeah, please ask questions. Ready to go? So keep that in mind. Powers, exponents, have an opposite operation. That's called roots. A few seconds ago with the 9 and the 3, those are called square roots. We also have something called cube roots and 4th roots and 5th roots. Yeah, it's not just all about the square root, okay? All right, next page. I'll explain myself in a moment. All right. So I'm going to introduce something new to you guys. They're called rational exponents. Write this at the top of the second page. Rational is referring to things that are fractions. And you know the word exponent also means powers. This is the crazy thing. It's not like I'm going to introduce a new operator, but I'm actually going to combine 2 operators together. Now, I don't know about you guys now. When I was growing up, I would eat peanut butter and jelly sandwiches. Some of you might be allergic to peanut butter, but I wasn't. Peanut butter jelly comes in separate cans. But this one company, I can't remember what the name was, decided to put both the peanut butter and the jelly together into one jar. Brilliant, I thought. And the actual jar was clear, and you saw the peanut butter and the jelly swirled inside the jar itself, like that. It was brilliant. Now, not for the kids who are allergic, of course, but you get the idea. The reason why I'm bringing this up is not because I'm hungry, is because we're introducing something called a rational exponent or a fraction power, because we're going to combine 2 operators together in a form that looks familiar called a fraction. And it's not a traditional fraction. Okay? Peanut butter and jelly jar has both flavors, right? We're going to do the same thing with, in this case, powers and roots. Here it is, ladies and gentlemen. We've already had product of a power, quotient of a power, power of a power, negative exponents, zero powers. Here it is, a to the, hold your breath, fraction power, m over n. This is weird. This is crazy. The top number in this fraction is the power, like peanut butter, and the bottom number is the root. Oh, that's like the jelly, right? Grape jelly usually. This is called a rational exponent. And please forgive me, I might shorthand the word rational to rattle and exp for exponent. We are going to play around with these problems, and sometimes we need to convert them back and forth between two forms. This literally means the nth root of a to the m power. This is called the radical form. Should look familiar, right? You guys are used to square roots. Square root of 9, 16. I'm sorry, 3. Square root of 25, 5. But square, meaning 2, can now also be represented by any root power. The root is here as part of the index, n. The power is out here, of course, above the base. We call this, again, let me write this down, the nth root of a to the m power. That's how you say that, okay? We're just combining peanut butter and jelly together in one problem. It's not a big deal. You know how to take powers? Great. We made a list of it earlier on in the other page. You know how to do roots, right? You're trying to break things down. And let's just start out with the baby one right here off to the left, okay? Here it is. It's going to look funny. 6 to the 3/4 power is how you say that. That's a rational exponent, also known as a fraction power a lot of times. This is a fraction form. Let's convert it right now to the other form. Write the radical first, write the base right there. The top number is the power, so slap it on right there to the 6. The bottom number is the index or the root. That goes right there, okay? That is the root or the index. Let me write that down. AKA index. All right. So now, when we put it into radical form, we can actually write it out and solve it, blah, blah, blah. We're not going to do that. We'll just convert it from one form to the other right now. This is called the 4th root of 6 to the 3rd power. That's how you say that. 4th root, meaning you need 4 numbers to come out. 4th root of 6 to the 3rd power. That's how we say that. If this is overwhelming, that's okay. Just take a deep breath and we'll walk you through this stuff. Now, the answer I just wrote, the 4th root of 6 to the 3rd power, you can also write it this way. So please, that cube power, the 3rd power, can be on the outside. It doesn't really matter. You can do it this way. They mean the same thing. Okay? All right. Let's take a look at number 1. We have, hey, how can you write the cube root of 2 using rational exponents? Let's write that down. Cube root of 2. 2 is the base, as you know. The 3, that little number right there on the radical, is called the root or the index. And where the heck is the power? It's actually invisible. If there's no power, assume it's 1. It's just invisible. And now we just have to convert it into rational exponent form, because right now it's in radical form. We're just going from radical to exponential form. Or fraction form. And all I have to do is write this down. 2 to the fraction 1/3 power. And that's it. Yay. That's your answer. Now, what does that mean? If you try to punch this into the calculator, the cube root of 2, it's actually approximately a decimal. And I'll write this down, 1.2599. That's all it means. That number will give you 2, okay? That number will give you 2 when you apply all the fraction powers. Great. Woo, kind of weird. Peanut butter and jelly. We're just combining powers and roots all together in one shot. All right, let's take a look at number 2 here. We're going to go ahead and use the properties of exponents and solve these rationals. This is going to be weird looking. Don't freak out, okay? Don't freak out. What is the solution to 2 to the x over 4 power times 2 to the x over 6 power equals 2 to the 3rd power? Holy cow, what's going on? Let's write it a little bit bigger so you can see it better. A lot going on here. I'm a little bit disappointed because I would rather take baby steps, but let's just walk through this as carefully as we can. First off, it's an equation, yeah? Second off, I notice that the bases are all the same, 2, 2, 2. But the one thing that screams out at me to work on first is the left side. What do I do when it comes to multiplying exponents? As you know, when we started this lecture, we had x to the 3rd times x to the 2nd. We just added the exponent, and that's the rule here. We're going to add the exponents. I know, how do you add x to the 4th over, yeah. Don't worry about it. We're going to do it symbolically first, okay? So let's show that. We're not going to actually add algebraic expressions that don't have the same denominator. That's just crazy. So here, it's going to be 2. We're going to add the exponents up there. X to the 4th plus x to the 6th. I haven't done it yet. I just rewrote it like that, okay? Now here, I can make the problem look better, a lot better. Notice that the bases are the same. Using the one-to-one property of exponents, I can now ignore the bases and just concentrate on the exponents and set them equal to each other using the one-to-one property. I can just say this. X over 4 plus x over 6, because, you know, it's all 2's already. You know, we don't have to worry about the base. It's the same. It doesn't matter. Equals 3. Wow. I know, this is crazy. To start off a new chapter with fractions, and we're not used to. I'm not a fan of fractions, but I'm a fan of shortcuts and how to get rid of fractions. You can actually get rid of 4 and 6 really quickly by multiplying by the least common multiple. The least common denominator of 4 and 6 is 12. So I'm going to pull out of the air. I'm going to do a cool trick. I'm going to multiply by the LCD in an equation, which happens to be 12, okay? It's a cool trick. It gets rid of all the fractions right away, and it's really nice. I'm gonna multiply this by 12, this by 12, all the terms that by 12. And what happens, it's really cool, is they reduce really nicely, okay? See the 12 and the 4? That reduces, woohoo! Yay, and the 6, that reduces as well. And of course, this makes my life so much easier. 3x plus 2x equals 36. You didn't know this, did you? Or maybe you've forgotten about this. My fraction disappeared because I did a trick called multiply by the LCD. Really, I love that trick because I don't like fractions all the time, especially with my, oh, where did that go? That was kind of weird. Ghost in the machine. Maybe I just wanted to delete. Oh, I pushed the wrong one. There we go. Okay, so 3x plus 2x, of course, is 5x. And that equals 36. Divide by 5 to both sides. Not too bad. And there's my answer, okay? Some random answer, x equals to 36 over 5. Don't worry about the answer itself, but that is the answer for the whole problem. Wow, kind of a weird opener for example 2 there. Very weird. We applied the product of exponents. Then we applied the one-to-one property. And then we applied a cool trick with fractions. Wow. Algebra 1, folks. Yeah, we're pulling all the tricks here. And then we did just solving that at the end. I mean, never mind the actual problem itself. Did you follow the logic here? I hope you did. Okay. Number 3, brace yourself. Example 3. We got some funny looking numbers here. And keep in mind, we just pulled out of the air the one-to-one property of exponents by concentrating on problems with the same base. Right up here, same base. Oops. Same base. So to do example 3, I want you to think about a base that we can take care of. Now, what scares me with example 3 is the number 256 and the number 4. You actually have 2 choices here. Let me explain to you about the number 256. All right. Number 3a is just like number 2, but the bases are different. That is scary. We want the bases to be the same so we can concentrate on the exponents and solving them. But because we have a 256 and a 4, we cannot solve anything yet until we pull that, change to 256, okay? Now, I'm not going to do magic here. What I want to do is think about the number 256. You may not know this, but you could break down 256 very, very far. The number 4 can stay or be broken down further. It's up to you. It really doesn't matter. You actually have 2 choices here in solving this problem. We can actually break it down to 4 or even further down to 2. Let's break down 256. If you didn't know this, that's okay. You can start dividing by 2. I don't care. But 256 is 16 times 16. 16 can be broken down further. It's 4 times 4. Now, I'm not expecting everyone listening to this lecture to just get that right off the bat. I'm going to stop. And say, hey, there it is. I have 4 4s. 256 is 4 to the 4th power. 4 times 4 times 4, right? Think about that. Make sense? 4 to the 4th power. Now, what was the 256 to a power of? X plus 2. Like that. Let's bring this down. Ooh. So what I did was I found the same base, the goal. Need the same base in order to eventually set the exponents equal to each other. Now, before I do that, though, I have to deal with this 4 to the 4th to the x plus 2. 4 to the 4th to the x plus 2 requires me to apply another property, power of a power right there. The rule for power of a power is to multiply the exponents. That is the rule. Okay, that was from way back earlier. So this is now 4 to the 4 times x plus 2. Now, if you don't believe me, it's multiplication. You need to go back to the first page. If you forgive me, we had early on, right here, power of a power, x to the 3rd and to the 2nd, you multiply the exponent. That's the rule, okay? So let me go back to example 3. Forgive me if I'm jumping around here a little bit. Okay. So now I have the same base. Woohoo! The base is 4 I can now concentrate on the exponents and set them equal to each other. 4 times x plus 2. It's just regular algebra at this point. This is crazy, huh, this lecture? You didn't expect to do so much new material, stuff you've done before, but thrown all together. We're just throwing the kitchen sink, the bath water, the refrigerator into this whole thing. 4 times x plus 2 distributive property. Let's go ahead and solve. I have x on both sides. I got to move those together first. And to save space, I'm going to move the 8 to the other side. I like to do that. Save a step. 9 minus 8 is 1. Dun, 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 dun. And that is your answer. Now, before I move on, I want to point out that the base 4 could have been broken down further. If you actually did it manually off to the side and just started dividing by 2, there's nothing wrong with that, okay? I just want to show you that this can be done this way too. Trying to do division in my head. And 4 didn't have to be used. You could have used 2. You notice those 2 right there? 256 is 2 to the 8th power. You could have used base 2 if you want to. And you can always break down the 4 over here to 2 squared if you want to. So that's one scenario you could have done, okay? Another way of doing that. All right. Let's try B. It's going to be weird. I'm going to warn you right now. Whoa. This is a very difficult problem. 1 over 8. 1 over 4. Don't let the fraction throw you out. This is a crazy problem. I'm kind of scared to show you. But I'm going to try. If you can follow it, don't worry about the actual fractions itself. Just see what I'm trying. I'm trying to get the same base. I have 1 over 8. 8 is 2, 2, 2. The 4 is 2 and 2, right? So that's the way that they both can meet. Now, if you're thinking that 4 goes into 8 equally, I understand that, but we're not doing multiples of 4 here, right? It's not 4 times 2. There's only one way to meet those two bases, those fraction bases, by 2's. So let me rewrite this problem. This is 1 over 2 to the 3rd to the power of x over 2, whatever the heck that is. Oh my gosh, this is already ugly. Over the other side is 1 over 2 squared. We're almost getting there. Isn't this crazy? Look at that. Okay. What happened to my graph? Oh, what's going on here? I don't know what's going on. Okay, a little glitch in the matrix, of course. All right, now 1 over 2 cubed is kind of weird if I'm trying to move that power to the outside. Now think about it this way. 1, I'm going to work backwards here. Doesn't change no matter what power you throw. I'm going to rewrite this thing as 1 over 2 to the 3rd power. Now that's kind of a weird move there. It's something we do in Algebra 2 and trigonometry. I know this is crazy. This looks like I'm migrating the 3. Now if you reapply the 3rd power to the 1, it's still 1. So I'm not really doing anything weird there. But this is a crazy problem that I gave you guys to use as an example. If I lost you right now, that's okay. Just follow what I'm doing. I'm just extracting that power of 3 on the left side and extracting that power of 2 on the right side. So that allows me to do power of power there and a power of a power there. Yeah? Running out of room there. So this is now 1/2 to the power of 3 times, using the power of a power, x over 2 minus 1 equals to 1/2 to the power of 2 times x over 3. I know, right? Whoever made this problem up, they were probably evil. Evil. Okay, the bases are the same. Nice. I can ignore them. I can just set the powers equal to each other right now. Okay? Okay. So how are we going to do this? Distribute the 3 first? Sure. We do that up here to save a little time. Distribute the 3. That's going to be 3x over 2 minus 3 equals, what was that, 2x over 3. I don't like fractions, do you? Looks like the least common denominator between 2 and 3 is 6. I'm going to multiply by 6 to everything. That's the LCD. It's a cool trick. It really is. So this times 6, that times 6, and that last one times 6. That saves a lot of time. It really does. So 2 goes into 6 3 times right there. That gives me 9x. Let me know if I need to pause, if I'm going too fast. 3 times 6 is 18. And over here, we have the 3 goes into 6 twice. And 2x times 2 is 4x. All right, the rest is solving that. Subtract 4x to both sides. I'm going to add 18 to both sides. To save myself some room there, some time. 5x equals to 18. And divide by 5 to both sides. Yeah, more fractions. And that's your answer. Don't worry about the problem itself, but kind of recognize what I was trying to do. Get the same base by extracting powers, breaking it down the bases so they can match up to each other. All right, we're going to skip the habits of mind at the bottom. Any questions? We're going to skip example 4 and 5. Woohoo! On the next page. Example 4, bye-bye. And example 5, bye-bye. We're going to jump to the last page. Thank you for hanging in there, of course. Let me start with number 7. We're going to write each radical using rational exponents. Right now they're in radical form. These are radicals, right? Radicals are the nth root of a to the m power, and we want to move it into rational exponent form, which is a to the m over n power. That's what we're trying to do, right? Okay. So right now that first one, number 7, is the square root of 7. It's a couple of invisible numbers, and you may not be able to see it. The square root of 7 has a couple of invisible numbers, and they are 7 to the first and the square root right there. That's what's hidden, okay? So let's write this as a rational exponent, also known as a fraction power. Yeah, and this is equal. This is becomes 1 over 2 power. And that's it. Yay! Now you know the secret. We're going to do the same for all these other ones. We're going to find our hidden power right there and a 2 right there. Nice. And let's convert. This becomes the base 15 to a fraction power. The power is on top, and the root or the index is on the bottom. This is 1. Oh, wait a second. Ladies and gentlemen, square roots are 1/2 powers. Something to remember, okay? Anything time you see a square root, think of 1/2 power. That is the answer. Okay. Number 9. These are pretty easy, huh? Base is 6, the power is 4, and the root is 3. That's it. We do have some improper powers, which is kind of interesting. You'll see more of that later on, why and how that works and how that simplifies. Number 10 is kind of weird. All right, whatever. The power and the index are the same. Literally 2 to the 3 over 3 power. Now, don't leave it like that. 3 over 3 reduces to 1 over 1. It's just 2. I mean, if you think about it, this is the cube root of 2 times 2 times 2. And that index 3 tells you need triple numbers to come out. That literally comes out as a single 2. And there's your answer right there. Oh, number 11 is the same. Kind of weird. Okay. I gave 2 of the same type of problems. This is 2 to the 4 over 4. This is literally 2 to the first power again. That was weird. Number 12. Let's write it into rational exponent form. This is a to the, oh, there's an index of a 2 there. That's a square root right there. We call it square root, so there's an invisible 2 there. A to the 3/2 power. Yay. And that's your answer right there. Now, I can technically write this answer down in other ways. If you're curious, do we have time? Okay, I sometimes I never know. I see the number 8 and that bothers me a little bit. Isn't 8 2 times 2 times 2, folks? 2 times 2 times 2 is 2 to the 3rd power. Whoa, to the 3/2 power. Whoa, using the power property, isn't it multiplication right there? Whoa, where's Mr. Chan going with this? This is going crazy. 3 times 3/2 power. You can see where this is going. This is 9/2 power. This is 2 to the 9/2 power. What? What is going on? Ladies and gentlemen, that answer is the same as the other answer over there to the left. FYI. Okay? All right. Any questions so far? All right. Let's take a look at, we're going to skip 13 and 14. We're just, oh my goodness, there's like 6 of these here. We don't really need to go crazy, huh? Let's go and pick 2 of these ones. We've already done plenty of fractions for the day. I think we could just focus on maybe 15 and 16 and then call it a day. Yeah, we've done plenty of hard ones in the actual examples over there. So number 15, I'm going to write a little bit bigger. I'm going to do 15 and 16. Let's do that. Okay. We have 64 to the x plus 1 equaling to 4 to the x plus 7. 4s and 64s are related to each other. Now, I'm not going to be here to try to explain to you how to break down 64 by 2s or 4s, but 64 is literally 4 times 4 times 4. If you didn't know that, let me show you this. Watch. Off to the side. 64 is 8 times 8. 8 is 2, 2, 2, 2, 2, 2. You can use 2s if you want to. In fact, you know what? Let's do 2s. Last time we kept it at 4s. Let's do 2 for both sides. So 64 is literally 2 to the 6th power because there's 6 of them. You all see that? 2 to the 6th power. Great, that's fine. No big deal. No big deal. No big deal. 2 to the 6th power to the x plus 1. 4 can be broken down to 2 times 2. That's fine. So this one right here is 2 squared to the x plus 7. Power. The rule for power of a power is to multiply those. Power here as well, multiply those right there. So this is 2 to the now 6 times x plus 1 on one side, and this is 2 to the 2 times x plus 7 on the other side. So with that in mind, the bases are now the same. Yay! And because of the bases are the same, just concentrate on the exponents and solve them like a regular equation. That's it. No, simple enough. So here, we're going to write this down. Oh, distribute. Let's save some room here. Distribute the 6 up there. Distribute the 2 over there. That's 6x plus 6 equaling to 2x plus 14. Let's solve this like a regular equation. Let's move the x's over to the one side and move the non-x's, the 6 especially, to the other side. Save ourselves some time here. 4x equals to 8. Divide by 4. Yay. X equals 2. I'd rather do that than fractions that we have crossed out from earlier. Hey, not too bad. Let's do number 16. Ooh, a lot easier. 16 is 4 times 4. Let's break that down. And 4 times 4 is 2 times 2 times 2 times 2. So yay. Zoom in a little more so you can see the things a little better. 16 is 2 to the 4th power. Okay. To the x minus 3 equals 2 to the x minus 6. I do need to apply the power of a power rule right there. Multiply those. In a moment. Now that I have the same base, I can just concentrate on the exponents using the one-to-one property of exponents. Yay, distribute the 4 to save myself a little time there. I now have 4x minus 12 equals x minus 6. And the rest is the same as what we did in the previous problem, number 15. Move all the x's to one side. And add the 12 to the other side. 3x equals to 6. Oh, yay, came out nice. No way. Did we get the same answer again? No. Sometimes it's kind of weird to get the same answer twice. Seems like it happened twice now on this page. Oh, yeah. Number 10 and number 11 happen to be the same as well. And there it is. Woohoo! That is your answer. 2. Woo! That takes care of 6-1, folks. Any questions? We just made it underneath an hour. I know this was lengthy. Well, anyway, thank you very much. Have a good day. See you next time. Bye-bye.